Hello everyone. So in this video we are going to learn about plate motions and their driving forces, and there are three lesson goals for this video for you to be able to describe the characteristics and classification of lithospheric plates, and to be able to describe the three types of relative plate motions and their examples, and lastly to be able to identify the forces that contribute to driving plate motions. So this is the present day configuration of the present day plate configuration of the Earth, and each of this colored region represents a tectonic plate. But what is exactly a tectonic plate? So in order to answer that question, let's take a look at this slide here. One thing that I have to mention is that tectonic plate is the same with the lithosphere of the Earth. And remember that lithosphere is a term that we use to classify the Earth's layers based on physical properties. So we are strictly speaking about the physical behavior of this layer. So again, lithosphere is the outermost layer of the Earth, and it is solid, rigid, and cannot flow. Okay, so if we take a look at this figure, lithosphere actually covers from this surface right here, from the surface all the way to this point right there. Okay, so that means that it covers the entire crust plus the upper side, the upper part of the mantle. And that's basically the definition of the lithosphere. There are two types of lithospheres that we know, depending on what type of crust that we have on the surface. So for example, if we have a continental crust, then we would call the lithosphere that in this section as the continental lithosphere or continental plate. If we had the oceanic crust on the surface, like in this side of this figure, then this will be called as the oceanic lithosphere or the oceanic plate. Okay, very easy. It's also very easy to distinguish them on cross sections. Continental lithosphere is typically much thicker than the oceanic lithosphere. Okay. Another thing that I'd like to mention here is also that the lithosphere overlies the asthenosphere, which is this red region right here. And remember that asthenosphere is the layer of the Earth that is soft, plastic, and it is able to flow. Okay. From map view, we can observe that some plates are entirely oceanic, and the good example for that will be Pacific Oceanic Plate. But others are made of both continents and oceanic lithospheres. Okay, and again, a great example for that will be the North American plate that we are living on right now. The land would represent the continent lithosphere, and everything in the Atlantic Ocean that would represent the oceanic lithosphere of the North American plate. An interesting observation that we can make is that if we take a look at these figures, these red dots, they represent earthquake locations or earthquake epicenters, and you can see that these locations are not random, right? These red dots are actually tracing the edges of tectonic plates. So if I go back and forth between these two figures, you can see that these red dots, they basically correspond to the edges of tectonic plates, and those edges are called plate boundaries. So there are three types of plate boundaries that you should know. The first one is called divergent plate boundary. This is when we have two plates moving away from each other. Okay. The opposite would be called convergent plate boundary, when we have two plates moving towards each other, or they're basically colliding. Okay. And the third one would be called transform plate boundary, when we have two plates slide past each other horizontally, just like illustrated on this figure right here. Excuse me. Okay, so in the previous video, we already talked about divergent plate boundary actually when we talk about seafloor spreading, right? Because we know that for seafloor spreading to occur, we need to have two plates that are moving away from each other, right? So that would be a great example of divergent plate boundary. And divergent plate boundary can move about 1.7 centimeter a year, but basically all the plate motions are moving in centimeter a year. It can be up to 5 to 6 centimeter a year, but this is probably the best average velocity of the plate motions on Earth, 1.7 centimeter a year. All right, the next one is so not only in the ocean, we can actually have divergent plate boundary in the middle of the continent. And the process is called continental rifting. That happens when a continent stretches and thins and eventually breaks apart into two separate continents, like illustrated in this figure. And this process happened in the past already, like 200 million years ago when the supercontinent Pangaea split apart. That process actually caused the North American continent, which is right there, to be separated from the African continent on the opposite side. So therefore, it creates that configuration that we are familiar with on the present day. And again, it not only, we also have the present day example of continental rifting, because if we take a look at the eastern side of African continent, so as we speak right now, the African continent is actually right now is actively splitting apart, okay, along a rift zone called the Eastern African Rift Zone. So that's very interesting, actually. The next one is called the next type of plate boundary is convergent plate boundary. Again, this happens when you have two plates moving towards each other. All right, so they are basically colliding. And there are a couple of examples that I'd like to show you. The first one, the first example represents convergent plate boundary when we have continental plate move towards the oceanic plates. Okay, so we have continent versus oceanic plates that are colliding. This process would produce one of the most prominent feature on Earth, which is called the subduction zone. Okay, subduction zone occurs when we have the oceanic plate goes underneath the overriding continental plate. Okay. Now, the reason why the oceanic plate goes underneath the continental plate is because of their composition. Remember that continental crust is mostly silicon and oxygen, whereas the oceanic crust is mostly, well, it does have silicon and oxygen, but it also has a high content of metal elements such as iron or nickel and other types of metals. So therefore, it makes the oceanic lithosphere much denser than the continental lithosphere. So therefore, when they collide, the oceanic lithosphere will go down, okay, underneath the continental lithosphere. Okay, so the process of consuming a plate is called subduction zone. Okay, so the process is called subduction. And here I have to mention this early, that subduction is associated with major geological processes, and in this figure it illustrates that it is associated with volcanic activity over here. The reason for that is because as this plate goes down underneath the oceanic plate, goes down underneath the continental plate, then the downgoing plate would be, getting hotter and hotter. All right, and it actually allows the partial melting of the downgoing plate that actually fuels the volcanic activity on the surface. But not only that, though, subduction zone is also commonly associated with an earthquake zone, which is called the Wadati Benioff zone. Okay, so this is the Wadati Benioff zone. It actually this zone records the deep earthquakes that are commonly associated with subduction zone. Another example, the second example for convergent plate boundary happens when we have oceanic versus oceanic plates. Okay, so the first one we had continental plate and oceanic. Now this time we have both oceanic plates that are basically colliding with each other. One of the plates must be denser than the other one. um, and the denser plate will go underneath the less dense plate. Okay, and again the same process occurs. We have subduction, and if we had oceanic versus oceanic plates, this process is typically characterized by the formation of volcanic island arc, which is very common in the Pacific Ocean. And the last example for convergent plate boundary is when we have both continent versus continental plates. Okay, so the process is called continental collision. Okay, continental collision usually starts after subduction has consume the entire oceanic plate that was once between two continental plates. Okay, so for example, in this figure, we have a little bit of oceanic plate right there, but eventually, as the subductions keeps going on, then this oceanic plates will eventually be entirely consumed by that process, and that would allow the two continents to basically collide with each other. And when this occurs, plates will undergo extreme compression and mountain ranges will start to form. And the best example for that will be the formation process of Himalayan mountain ranges, and this is the animation for that. So as you can see here, it starts from the normal subduction when we have the oceanic plate goes underneath the continental plate, and then eventually the subduction consumes the entire oceanic plates, and these two continental plates starts to collide. So they collided and they form mountain ranges. The reason for that is because when you have two big gigantic continents that are colliding with each other, both of them are actually very buoyant, so they don't allow subduction process to continue. And the third one is called the transform plate boundary, and again this happens when we have two plates slide past each other, like illustrated in this figure right here. You can see this block moves that way, and the block on the other side moves on the opposite way. Okay, here there's no destructions of older plates or creation of newer plates. Okay, so no new plate forms and no old plane is consumed along transform plate boundary. And the best example, one of the most famous example on Earth, is basically San Andreas Fault, which is in the western part of the United States. Okay, here we have two plates, Pacific plate on in the west, and we have the North American plate in the east. Pacific plate is actually moving towards the northwest relative to the North American plate on the other side of that boundary. Okay, so basically they're moving, boom, like that. Oh no, oh man. Okay, like this. All right, so that's an example of San Andreas Fault for transform plate boundary. All right, the next thing that I would like to talk about is about the mechanisms of plate tectonics. Okay, because remember, we already learned about Alfred Wegener's continental drift theory, but the unfortunate side of this is that he failed to explain how the continents move. Right, so in modern science, we should be able to address that concern. So there are three plate driving forces that we know. The first one is called mantle convection, the second one is ridge push, and the third one is slap pull. Okay, so let's talk about the mantle convection first. When I first learned about mantle convection when I was an undergrad, they always show this picture right here, but new studies actually suggest that the mantle convection is not as simple as this, okay? Because here it looks like a very simple model, but it turns out that it's much complicated than that. Okay, so now we know that in the mantle of the Earth we have some colder regions, much colder than this region, for example. Okay, so the convection cells are not big as illustrated, uh, you know, 10 years ago. Anyway, so convection flows within the asthenosphere may drag along the overlying lithosphere. So even though we do have some colder regions in the mantle, but these cells right here could still produce mantle convection, and that flow of the asthenosphere and the rest of the mantle underneath the lithosphere could possibly drag the overlying lithosphere with it. Okay, so that's the first driving force, mantle convection. The second driving force happens um, in at mid-ocean ridges when we have the seafloor spreading. Okay, so the ridge push occurs at mid-ocean ridges, and it is an outward directed force from the mid-ocean ridge. The reason for that is because mid-ocean ridges, they stand tall, much taller than the abyssal plain on the opposite sides. Okay, on both sides of the ridges, and the elevation difference can be up to 10,000 to 20,000 feet. So it's actually pretty significant. So these elevation differences, eventually, these lithospheric plate will cool down and then will sink, right? And when they sink, they actually would push the adjacent oceanic plates. So therefore, that forces, that is what we call as that gravitational energy, that's what we call as the ridge push. Yeah. And the third one would be called the slap pull. And slap pulls occurs at subduction zone. The older and colder sinking slab, just like what I'm showing you right here, this would be much denser than the underlying asthenosphere, so it simply sinks to the bottom of the mantle. So I think that is all that I would like to say in this video. Again, if you do have questions, let me know, and I'll see you again in the next module. Bye bye.